In the narrow strait between Java and Sumatra, a volcanic island holds a secret the world is not yet ready to see. The year is 1883, and the Sunda Strait glitters under equatorial sunlight, a paradise of green slopes and blue water. Dutch colonial ships navigate these lanes daily, their logbooks filled with the routine observations of a peaceful sea. Krakatoa rises from the ocean in 3 forested peaks, home to birds and wildlife, its geological violence long forgotten. Local fishermen read these waters for generations, decoding currents and wind with the precision of inherited knowledge. Spice trade routes centuries old pass within sight of the island's slopes, indifferent to what sleeps beneath the rock. Yet beneath this tropical idol, something ancient and immeasurably powerful is slowly, inexorably beginning to wake. How does a tropical paradise become the epicenter of the most violent geological event of the modern era? What the world is about to witness will rewrite geology and change how humanity understands the planet itself forever. The island is about to become the most consequential geological event of the 19th century, and no one knows it yet. The warning signs begin months before the catastrophe. Subtle at first, easy to dismiss as ordinary volcanic activity. In May 1883, columns of steam and ash rise from the island's northern peak, visible from passing vessels miles away. Ships' captains record unusual atmospheric disturbances, a sky that seems heavier, more charged than it should be. Fine gray ash settles on the decks of merchant vessels transiting the strait, coating ropes and canvas with pale dust. The colonial authorities in Batavia receive reports, but find little cause for alarm or any immediate evacuation orders. Krakatoa has shown signs of unrest before. The regional memory of eruptions is measured in centuries, not in years. The colonial press in Batavia prints brief notes about increased volcanic activity, then returns to commercial affairs. Sailors who pass too close to the island report a persistent, sulfurous smell hanging over the water for miles around. Volcanic gases affect compass readings on ships in the strait, creating confusion among experienced navigators. But the pressure, building inside the mountain's magma chambers, follows no human calendar and respects no authority. By July, the eruptions grow more insistent, the columns of ash and steam reaching higher into the tropics each week. The deep roar of subterranean explosions travels across the water at night, unsettling every coastal community nearby. Navigational authorities issue shipping advisories. The strait sees reduced traffic, but commerce does not fully stop. A Dutch government surveyor visits the island in August and finds a landscape transformed entirely beyond recognition. He notes that the soil temperature has risen dramatically and that 3 active vents now expel enormous quantities of ash. The forests that once clothed its slopes have vanished entirely, replaced by lunar fields of gray and black volcanic rock. The sea around the island churns with unusual colors, chemical signatures of deep subterranean activity rising upward. The surveyor recommends that shipping avoid the area entirely. The colonial government begins to take note of the risk. Scientists and engineers in Batavia debate whether the island poses any real danger to the nearby populated coastlines. And yet nothing in human experience has prepared anyone for what the island of Krakatoa is actually preparing to do. By the final days of August 1883, the question is no longer whether Krakatoa will erupt, but what scale it will reach. The morning of August 26, 1883, arrives with a detonation that rattles windows in Batavia, 160 kilometers away. Ships in the strait struggle against an increasingly agitated sea, their compasses behaving erratically in charged air. Darkness spreads across the sky in the early afternoon, a growing veil of ash and pumice cutting off the sunlight. The SS Loudest, carrying passengers through the strait, navigates in near total darkness at 2 in the afternoon. Pumice stones begin falling from the sky, forcing crews to shelter below decks as the barometric pressure plunges. Radio communication does not yet exist. Every ship in the strait is entirely isolated from news of any kind. The captain of the Loudon later describes in his log a darkness absolute, broken only by continuous volcanic lightning. Lightning from the electrically charged atmosphere strikes the water in dramatic bursts that persist throughout the night. By evening, on August 26th, the Sunda Strait has become an arena of geological forces without any historical precedent. The morning of August 27th, 1883 begins at 5:30 a.m. with the first of 4 catastrophic paroxysmal eruptions in sequence. At 6:44 a.m., a second massive explosion sends a column of ash and gas soaring into the upper atmosphere above Java. Dawn on August 27th reveals a sky the color of iron, the air thick with fine ash falling like gray snow on the water below. At 10:02 a.m., the third and largest detonation occurs, permanently altering the geological map of the entire region. The sound that emanates from Krakatoa at that moment is, by scientific reckoning, the loudest noise in recorded history. A fourth detonation follows minutes later, completing a sequence of geological violence that finally exhausts the island. The pressure wave from the explosions travels outward in all directions, compressing the very air into a measurable pulse. That pulse circles the entire globe 7 times before instruments finally cease recording. One sound, one whole planet. Barometers in Calcutta, Honolulu, and Buenos Aires spike and fall in sequence as the pressure wave passes each city. The sky above the Sunda Strait turns black at midday, a darkness that witnesses later compare to a total solar eclipse. On the island of Rodriguez, nearly 5,000 kilometers away in the Indian Ocean, the explosion is heard clearly. In the Australian outback, in the jungles of the Philippines, along the coasts of Sri Lanka, it arrives like artillery. What follows the last detonation is not silence, but the beginning of an entirely different and deeper catastrophe. The sound alone represents an energy scale that defies ordinary comprehension, and it is only a fraction of the whole. Beneath the explosions, the island's magma chamber has catastrophically emptied, and the land above it collapses inward. 2/3 of the island of Krakatoa, an entire volcanic mountain system, disappears beneath the surface of the ocean. Where solid land stood for millennia, the sea rushes into a newly formed crater nearly 300 meters in depth. The volume of material expelled during the eruption is estimated at approximately 21 cubic kilometers of rock. This geological event, measured in minutes, redistributes a mass of Earth equivalent to millions of ancient structures. In less than 3 hours, the surface of the Earth has been rearranged in ways that charts will not reflect for months. The collapse of the island into the sea unleashes an energy transfer of a different and equally devastating character. The ocean above the collapsing crater is displaced by forces the concept of a wave can barely begin to capture fully. Walls of water rise from the sea at heights reaching 30 meters, a 10-story building moving horizontally at speed. The energy contained in these moving walls of ocean water is equivalent to the combined force of thousands of explosions. These waves travel through the Sunda Strait at the velocity of a jet aircraft, carrying vast quantities of kinetic energy. The towns of Merak and Anyer on the Javanese coast are reached in minutes, the tsunami arriving without any warning. Teluk Beton on the Sumatran shore faces the same fate as water surges far beyond any natural coastal boundary line. The colonial record lists over 300 coastal settlements affected along the shores of both Java and Sumatra. The lighthouse at Anyer, built to guide ships safely through the strait, vanishes entirely in the initial water surge. A Dutch naval vessel, the Barrow, is carried by the tsunami nearly 3 kilometers inland, up a Sumatran river valley. Survivors on higher ground watch the sea withdraw toward the horizon before the walls of water surge back inland. The human toll accounts for most of the 36,000 lives lost across the full extent of the catastrophe. The waves cross the Indian Ocean and are recorded by tide gauges in Ceylon, the Arabian Peninsula, and South Africa. Even in the English Channel, over 15,000 kilometers from Krakatoa, sensitive instruments detect the passage. That morning leaves a permanent signature in every ocean basin on the planet, its tidal imprint traceable across 4 continents. The eruption's effects on the atmosphere, however, prove to be just as far-reaching as its impact on the sea itself. The eruption column reaches an altitude of approximately 80 kilometers, injecting material into the stratosphere. This is not ordinary volcanic ash that rain can wash from the sky within a few days or weeks after a normal eruption. Fine sulfur dioxide particles combine with water vapor in the upper atmosphere, forming aerosols that encircle the planet. In the weeks after August 27th, these aerosols spread in both directions, from the tropics on high-altitude wind streams. The global average temperature begins declining as the volcanic veil reflects incoming solar radiation back into space. Scientists later calculate that the eruption lowers global temperatures by approximately 1.2 degrees Celsius for a year. Harvests fail in unexpected regions. Frosts arrive early in temperate zones, and meteorological records show anomalies. The summer of 1884 across much of the northern hemisphere is marked by unusual cold and persistent atmospheric unrest. The volcanic winter introduced by Krakatoa becomes, in the following decades, a recognized category in climate science. These atmospheric particles produce optical phenomena of extraordinary intensity, transforming skies across the entire world. Sunrises and sunsets become spectacular in ways that observers struggle to describe adequately in any human language. Shades of deep crimson, violet, and orange appear long after sunset, lasting sometimes more than an hour in the western sky. Observers in Chile, in Russia, in Japan, and in Australia all record the same breathtaking atmospheric color displays. Communities across Europe, North America, and Asia observe these extraordinary skies with wonder and genuine apprehension. In Connecticut in 1883, fire brigades respond to what residents believe is a massive, distant urban fire on the horizon. In London, artists and writers fill notebooks with descriptions of skies they have never witnessed in an entire lifetime. The Norwegian painter Edvard Munch will later cite these blood-red skies as an influence on his most enduring artworks. For the scientific community, the eruption offers an unprecedented opportunity to study atmospheric dynamics globally. The International Network of Meteorological and Barometric Stations in 1883 is just sufficient to capture the event. Scientists in Britain, Germany, and the United States begin exchanging measurements and observations without delay. The post-Krakatoa sky becomes a shared spectacle, perhaps the first natural event observed simultaneously across continents. But there is another network in place in 1883 that transforms this disaster into something historically unprecedented. The undersea telegraph cable network now connects most of the world's major ports in a web of electrical signals. Batavia maintains telegraphic connection to Singapore, which connects to Madras, Aden, Suez, Malta, and on to London. Within hours, news of the catastrophe travels electrically along these cables toward the editorial offices of Europe. The Times of London carries reports of Krakatoa within days, reaching readers thousands of miles from the event itself. For the first time, a natural disaster of global scale is reported to the wider world, while it is still occurring. Previous eruptions, Tambora in 1815, Laki in 1783, became known only through the slow diffusion of travelers' tales. The global information network carrying news of Krakatoa is itself a product of the industrial age at its height. Krakatoa enters global consciousness almost instantly, its name becoming synonymous with geological catastrophe worldwide. The Royal Society in London organizes one of the first comprehensive scientific investigations of any natural disaster. A committee assembles. Data is gathered from dozens of countries, and in 1888, a landmark scientific report is published. This report establishes methodologies for studying volcanic events that remain foundational in geology to this very day. The concept that a single eruption can affect global climate becomes, after Krakatoa, an established scientific principle. New fields of inquiry emerge: atmospheric chemistry, global meteorological teleconnections, the science of sound travel. The event redefines what science knows and what it can know about the forces that govern the surface of the Earth. The colonial administration undertakes a systematic effort to document the destruction along the coasts of both islands. Villages are reconstructed on higher ground. The experience of the tsunami permanently changes how communities plan safety. The navigation charts of the Sunda Strait require complete redrawing. The seabed and island geography have wholly changed. The island remnants of Krakatoa, stripped of all life, become one of the first documented cases of ecological recolonization. The question of how species colonize pristine volcanic terrain becomes one of ecology's most intensively studied problems. Within decades, plant life returns, then insects, then birds, transforming sterile ash fields into functioning ecosystems. The Krakatoa investigation sets a precedent for how nations share scientific data across borders in the face of planetary events. Scientists travel from Europe and North America to study the process, shaping early ecology as a recognized discipline. Krakatoa becomes, against all expectation, one of the most important natural laboratories in the history of biology. The speed of the island's ecological recovery challenges every assumption about how life reestablishes itself from zero. In this sense, even destruction on a geological scale carries within it the seeds of a different kind of beginning. In 1927, almost half a century after the eruption, something extraordinary begins in the waters of the old sunken crater. The shallow sea above the collapsed caldera begins steaming, and small eruptions send plumes of ash above the waterline. A new volcanic island rises from the seafloor, built by the same deep magmatic forces that destroyed its predecessor. The Indonesians name it Anak Krakatoa, the child of Krakatoa, a testament to cycles that exceed human comprehension. Anak Krakatoa grows steadily in the following decades, adding material to its cone with each successive eruptive phase. The very existence of this new island demonstrates that volcanic archipelagos are not fixed geography, but perpetual process. Volcanologists from around the world establish monitoring stations to study the young volcano's growth and behavior closely. The new island stands as living proof that the geological forces of 1883 have not ceased. They have merely been paused. In December 2018, Anak Krakatoa collapses again, generating a new tsunami along the Javanese coast without prior warning. The eruption of August 27, 1883 marks a genuine inflection point between human civilization and the natural sciences. Before Krakatoa, the global reach of volcanic events was understood in theory, but never documented across all continents. After Krakatoa, the world has both the will and the tools to monitor geological behavior on a truly planetary scale. The atmosphere is a globally shared system. One eruption in the tropics alters weather patterns across every continent. The telegraph cables that carried news of Krakatoa are the ancestors of every information network that has followed. A volcano that destroyed itself in one morning gave the world an understanding it could not otherwise have gained so fast. The roar that circled the Earth 7 times in 1883 still echoes, in a sense, through every field of Earth science today. If the story of Krakatoa moves you, explore the geological events that continue to shape the world we think we understand.